from last time? Or the time before? Or not the time before that, but the Tuesday before? No? Okay, good. No. Nope. Um, so last time we finished talking about the general method for structures, but this is something that just takes a lot of practice. And so I'm going to do an example problem up here, and then you all are going to do some problems working together. And as I'm doing this example problem, I think it's really helpful to try to, follow along, like see if the decisions I'm making make sense to you as we go. Okay, so here's the problem. We have a pin joint connected to the wall. But that's supposed to be a right angle. And at the midpoint of this member, we have some kind of a roller. And each of these length, oh no, this length is 1 meter.
Those are all pin joints?
Yes. And let's put the coordinate system here. And then, so we're going to neglect gravity on this one. Somebody asked me how to know when to neglect gravity. On these kind of problems, if I say anything about the mass of the object, the only reason you use that in statics, I believe, is to calculate the weight. So if I give you the mass or the weight, then you're using gravity, putting gravity in it. If I don't put it in, then you're ignoring it. Why would you neglect gravity? Like if you're trying to estimate a problem, you see some structure put together outside. When would you neglect the weight of the members?
If we're looking at it from above?
That's true. Yep, that's true if you're just looking at a plane that doesn't have gravity in it. But there are other times too. Like we're going to neglect the weight in this case, and this is, I'm picturing this as being from the side.
It could be negligible.
That's right. That's usually the key in statics things, is there's a weight, and it's not, it's big on our scale, but we're often talking about other external loads that just sort of dwarf those weight loads. Okay, so as an approximation, you just leave them out. Okay, but if you're ever in doubt doing a real problem, then put some estimate of the weight in. And okay, so that's 1 meter. And then there's a load acting at 90 degrees from this member of 5,000 newtons. And we want to calculate the reaction loads at those joints.
Did you say the roller was right in the middle?
Yes. Yeah. What are the loads on each member? At the pins. Oh, I did put up new practice problems, speaking of homework. So get to those as soon as you can. And I got to get some solutions up. I also put up one set of solutions recently, but I think there's still two I need to put solutions up for. Okay, so what are the steps for solving this? What's the first step? Yep, isolate the whole structure. And we're going to use Newton's second law in the rotational version to get three equations from the whole structure. Yes, number all members. That's step 0. I know I renumbered in my head. Try to stay with me. Okay. So step 1, number the members. Did that. Step 2, isolate the whole thing. So free body diagram. There's the free body. And what are the loads acting on the free body?
Full force on the pin.
Over here, yep. So we'll call that, I said that it's not, this is a step where it's not super crucial to use that AB notation, but it doesn't ever hurt anything. So I guess I'll call that the force on this body, and it's, I'll get to that in a second, and it's applied by the pin, okay, or the wall. I guess that makes more sense in the way I'm going to think of it. So what member is it applied to? So yeah, it depends on your convention that you're using. So we have a couple of choices. We can treat the pin as if it's its own member, right? Yeah, that's just adds extra equations, extra variables. So the way I said to do it is assume that that pin is part of member 1, okay? So I'm going to do that. So this is a force then on member 1 applied by the wall. Any questions about that? Is that confusing to anyone? I mean, this question is sort of at the heart of the most confusing stuff in this, using this method, right? This is what you have to iron out in your own head before you can really do this stuff. Okay, what other forces? What other loads? Okay, and what kind of force is that? Yep, that's right, vertical force. And that's a force on member 3 by the floor. And anything else? Yep, that's right. Pancake artists, row 4, marzipan. What is marzipan? I know it's an important thing in pancakes. Marzipan pancakes. Marzipan cakes. Okay, yeah, okay. I knew you needed them in pancakes. Anyways. Okay, so first, let's, oh, I did something I told you not to do here. Whoops. We know the direction of this force, right? So I'm just gonna name that. So that makes this a scalar variable, and since it's a scalar variable, you don't use that AB notation, okay? So sorry about that, but this, I'll just change that to R. Okay, so let's deal with that force R first. In this coordinate system, the length of this member is 0.7071. So the location of R is 0.35360. Right. For the about point, let's put it up here so we can get rid of this in our moment calculation. Okay, so I'm going to put it at 0, positive 0.7071. So rho is 0.35. That's different. Well, I'll do it this way anyways. That's different than I did it in my notes. And then negative 0.7071. The force is 0R. And so the moment applied about this point is 0.3536 R. And now let's do this 5,000 Newton force. Just to make the math a little simpler, this you can move anywhere along the line of action, right? So I'm going to move it down to the origin. Okay. So we'll say that that acts at 0, 0. So that makes rho 0, negative 0.7071. The force vector is negative 35, 35.5, negative 35, 35.5. And then you get that must be negative 2,500. Negative 0.7, so 0.7071 times 3535 is at 2,500. And be careful with the signs. So that would be positive, and then you're subtracting it. So negative 2,500. And that does make sense, because if you have a hinge here, this force is going to rotate the body clockwise, right? It should be a negative moment, right? And then this force, it acts at 0.7071. The about point is 0.7071. So rho is 0. The force is F1WX, F1WY. And so the moment is 0. So Newton's second law says, bless you, 0R plus negative 3535.5, negative 3535.5 plus F1WX, F1WY is equal to 0, 0. And the rotational equation, 0.3536 R minus 2,500 is equal to 0. Okay, so we have three equations. F1WX is equal to 35.5. F1WY plus R is equal to 35, 35, 0.5. And then 0.3536 R is equal to 2,500. And what do we have for variables? F1WX, F1WY, and R. Okay. So right now, as a sort of to cut down the size of the big matrix equation you get at the end, you have 3 equations, 3 variables. You won't be done with the problem because you haven't solved all the things you need yet, but you could solve this for these 3 variables, and that'd just cut down your number at the end. Okay, step 3, I guess. What's step 3? We're done isolating the body, the whole thing. So now we're going to isolate the individual members, right? So let's do the vertical member. And again, this free body diagram, like figuring out what loads are acting on what, is really that's the crucial step in this whole process. So what are the external loads acting on this vertical member? Okay, so that's true, and sort of the key is figuring out how to label these, like, and that all goes back to what you're considering the pin to be a part of, right? So, okay, what do we have here? We have, okay, so up here at this pin, right? That pin is part of the member that I'm isolating, right? This is member 1, the lowest numbered member, right? So on that pin, there are actually 2 things applying forces, right? The wall and member 2. Okay? Does that make sense? Anybody have a question about that? If you miss that, then you get this big system of equations. So miss one thing like that, every single force is drastically wrong. Okay? So we have one force vector on body 1 by the wall, and we have one force vector on body 1 by body 2. And what other loads are applied? Right. On 1 by 3. Okay. So that's a complete free body diagram, and if we were including weight, we'd put a weight force acting at the center. Okay. I guess let's calculate our moments about this point up here, because that gets rid of the moments produced by 2 force vectors. So let's deal with these 2 first. Those are applied at 0.7071. Let's make that the about point. So rho is 0, 0. I guess the first one I'll put in is F12. No moment. And next, F1W. It's applied at the same point. The about point is the same. So rho is 0. F1W. So 0 moment. And then F13, that's applied at the origin. The about point is still 0.7071. The rho vector is 0, negative 0.7071. F13x, F13y. And that gives positive 0.7071 F13x. So Newton's second law says F12x, F12y plus F1wx, F1wy plus F13x, F13y is equal to 0, 0. And the rotational equation just says 0.7071 F13x is equal to 0. Well, so if you happen to be like keeping track of how to simplify all this system of equations as we go, there's another variable that you know and another one you can eliminate when you do the big matrix at the end. So what's the next step? Now we have Newton's second law and the rotational equation. Yeah, so now we have to reduce the number of variables, make sure that we aren't calling redundant information by two different names. So let's see, what do we have here? Before we started this, we have 1W and R, and here we have 1W, right? So we don't have to switch anything. We don't have to use Newton's third law. So I'll just write these as equations 4, 5, and 6. So F12x plus F1wx plus F13x is equal to 0. Equation 5, F12y plus F1wy plus F13y is equal to 0. And equation 6, 0.7071 F13x is equal to 0. And now the variables. So we still have from before, we know we're going to have at least all the variables we had before. So 1wx, 1wy, and r. And now we're adding to this list F12x, F12y, and F13x, F13y. Okay? So right now we have 6 equations, 7 variables. And now let's isolate the diagonal member. What loads are acting on that? Yep.
Full force on both ends then.
And what are they applied by?
Well, it's F21 on the top and F23.
Right. So this pin here, so this member is only touching the pins, right? It's not touching the beams, whatever. So you have to consider what member those pins are a part of. Okay, so this pin is a part of member 1, so the force being applied by that pin is F21, right? On 2 by 1. And down here, this pin is part of member 2, right? There's a force being applied by member 3 to the pin, so that's F23. Okay, that's everything. As the about point, I'm choosing this point where F21 is applied. Remember, you can choose, like, for each body that you isolate, you can choose independently what your about point is. It looks like I chose the same one maybe for all 3 of those, but you don't have to do that. So let's start with the force at that point. It's located at 0.7071. So rho is 0. The force is F21x, F21y. So no moment. And then this 5,000 Newton force, we know the force is negative 35, 35.5, and negative 35, 35.5. And we could go through all this, figuring out the vectors and stuff, but you could also just notice that this force is perpendicular to a distance of half a meter, right? So we can skip all this other stuff and just consider this. It's going to produce a clockwise moment of negative 2,500. And then F23 is applied at 0.70710, about point 0.7071. So the rho vector is 0.7071, negative 0.7071. The force is F23x, F23y. And so you get 0.7071 F23y plus 0.7071 F23x. So we get F21x, F21y plus negative 35, 35.5, negative 35, 35.5 plus f23x f23y equal to 0, 0. And the rotational equation says negative 2500 plus 0.7071 f23y plus 0.7071 f23x is equal to 0. Okay, so now we have to reduce the number of variables. So the variables that appear in these equations are the f21 vector, the f23 vector. I guess that's all, right? So now we're going to look back at our previous list of variables and see if any of those occur in their switched form, right? Like if we have to use Newton's third law for any of these. So we do have f12. We don't have f32. So that means that equation 7 is going to be negative f12x plus f23x is equal to 35, 35.5. And equation 8, negative f12y plus f23y is equal to 35, 35.5. And then 9, .7071 f23x, I'm just switching the order of these two for the matrix, plus 0.7071 f23y is equal to 2500. And our list of variables, we have r f1w f12 f13 and then we also have f23. Okay, so 9 equations, 9 variables, right? Yep. So now we can solve it. Okay, let's see here. So let's do it in this order. Okay, so there's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is going to be the augmented matrix. This will represent equation 1, equation 2, 3, 4, 5, 6, 7, 8, 9. And this will represent R, F1WX, F1WY, F12X, F12Y, F13X, F13Y, F23X, F23Y, and this is that constant vector on the other side. So our first equation is F1WX is equal to 35, 35. F1WX, just one of those, is equal to 35, 35.5. And everything I don't fill in is zeros. Equation 2 says 1WY plus R is equal to 35, 35. So 1WY plus 1R is equal to 35, 35.5. Equation 3, 0.3536R is equal to 2500. Okay. Equation 4, F12X plus 1WX plus 13X equals 0. Okay, so 12X, 13X, 1WX is equal to 0. Then 12Y plus 1WY plus 13Y equals 0. And you always get a lot of those in these matrices where you'll have just shifted, value shifted over one spot because you have the x equation and then the y equation that often has those same variables, just the different component. You know what I mean? These are the x, these are the y. And then 0.7071 13x is equal to 0. And now we're on the last three. So negative 12x plus 23x is equal to 35, 35. And then we have the y version of that. So shifted, 35, 35.5. And then the last equation, 0.7071 times 23x let's see. 7071 times 23y is equal to 2500. Has anyone already solved that? Okay, can someone punch that in? I guess I don't have that written down. Yeah. Okay, so we got tell me if you guys get this same thing. We got R equals 70, 70. Some round off error, I guess, there. And then F1W is equal to 35, 35, negative 35, 35. F12 this says 0. F12.
Negative 35, 35 over.
Oh, yeah, okay. Over 0. Or something close to 0.
Oh, no, I didn't get that.
You didn't?
I get positive 35, 35. So negative 35, 35
Okay.
over positive 35.
Huh. Anyone else get an answer for that? Let's see. Well, let me look at that. So 1, 2. Yeah, there's nothing to eyeball really there. Anyone else get an answer for that one? What? For this is the 1, 2, 3, 4, fifth variable down.
0.0678.
Okay, that's what I got here. And then F13 is 0, 35, 35. And F23 is 0, 35, 35. Anyone else get that? Okay. All right, so how do we use this now to determine what the external loads are on each of those members? Okay, because these, so far this doesn't mean anything until you think of these as forces acting on an object. So we have these three bodies, and you can always refer back to the free body diagram to see what the meaning of these are on each individual body. So when we isolate that first member, we have F1W plus F12 acting up here, right? And we have F13 acting down here. So 35, 35, negative 35, 35. And we also up here have F negative 35, 35, 0. And 1, 3, we have 0, 35, 35. Okay. There's one thing that we can use now to make sense out of this. Like, does this look plausible? Like, what can you look at here to tell you whether this makes sense? That's right. They all add up to 0, 0. And there's one more thing about this. This is a two-force body, right? If you add these two up, it gives you a force at one end, and this one gives you a force at the other end. So each of those those have to be equal and opposite going from one point to the other one. Otherwise, this thing would be rotating, okay? And you can see if you add these up, you get a downward force and an upward force. So that all makes sense with a two-force body. Okay, so that's always a useful thing to look for, I think. Look for where you have two-force bodies and make sure that your forces are lining up the way they should. By the way, while we're talking about that, so is that in compression or tension? Is that being stretched or squished? Right. And now isolate the diagonal body. We have F21 and F23. And we have this 5,000 Newton force. F21 is the opposite of F12, so that's positive 35, 35, 0. And F23 is 0, 35, 35. And that makes sense if you think about the moments that these different things are producing. So that body's in equilibrium. And then the last one, we didn't isolate that one, right? But we have R acting here. And we have F31. It's going to be equal and opposite to F13. So we got 0, negative 35, 35. And then this is F32, equal and opposite to 2, 3. So we have 0, negative 35, 35. Okay. So this member is going to, like, the strength of that material is going to try to keep this from squishing down to nothing, right? The strength of this material is going to keep it from bending. Can you picture that? It's like you have two forces acting on the sides, fighting against a downward force in the middle, right? And that's the same thing that's happening here. So two of these members are resisting bending. One of them's resisting compression. Any questions about that problem? Okay. This feels like it's making pretty good sense. I think think about two things as you do these. So getting the right free body diagram is everything in these problems, okay? If you get your free body diagrams labeled right, then everything else is just, following steps. And I guess as an aside from that, like a part of that is, so you kind of have this natural reaction that comes from the physics that you've done before, where you think, like, to describe a free body diagram, say, like, we're isolating this member, what loads are acting on this? And you think, like, okay, there's a pin joint, so there's a full force vector there, a full force vector there. But that's only part of the story, The real story, like, you're not out of the woods on this free body diagram until you get those labels right, okay? If you get the numbers switched or something, or get the bodies wrong, everything will be wrong, okay? Okay, so here is a problem for you to work on. I know you've been waiting.
I have one question. Wouldn't the diagonal beam be in a little bit of tension?
Yes. Yes, that's right. Exactly. Is it tension? I guess it's a little bit of compression, actually, right? You have the horizontal force pushing this way. But yeah, that's exactly right. You got sort of a component of this compression thing, and you have a little bit of this bending thing. And we'll talk about how to calculate that. It's a complicated issue to deal with that stuff. It changes all the way along, like what the internal loads are, and we'll talk about that at the end of the class. You know, like if you have an object like this and you subject it to this loading 1,000 times, you know, in parallel universes, you have the equipment for that? Yeah. Okay. It's going to break in the same way, the same place every time. So why is that? It's because if you calculate the internal loads, they suggest, you know, a chance of failure at a certain spot, you know, and we'll figure out how to do that later on. All right, so you're going to calculate, so this is outside the Hall of Justice. They have, well, not the Hall of Justice, because that's DC Comics, I think, but they have this statue of the Figure Four. What's that group called? The Fantastic Four, yeah, the Figure Four. And they want to hang they want to hang a weight from it that applies a 20,000 Newton force, mostly laundry, for that rock guy. Yeah, he does. That doesn't come across in the drawings, but yeah, he does.
That's one member all the way through the bottom, or on the horizontal?
Yes, that's right. And these are all pins. This is a fixed joint. And the full length of this is 1 meter. This is the midpoint. And then you got the same thing here. So what are the external loads on each of those members? Okay? And feel free to talk out loud and talk to people around you and just try to work through this. And I think it's a good habit to get into, to, like, if you don't have those steps in your head, then look back at them and make sure you're following the steps, you know? We want to make this sort of as systematic as we can, so you're doing the same thing every time.